My name is Hannes Reuter. Here I'm your host for today, and Geoinformatician is an international society which looks into the science of quantitative land surface analysis, and we are a non-commercial, non-governmental association of researchers around the globe, and we're trying to understand or improve the understanding whatever you can do with a digital elevation model. We try to advance techniques, foster international collaboration for quantitative analysis of the land surface, and trying to bridge even the gaps between scientists, data producers, policymakers, and trying to bring all these people together. And with that one also, we have here our coffee talks where we have a variety of presentations, like the last one where we talked about software. Now today, again, we have a talk about a data set. So we're trying to bring in a wide variety of topics into our coffee talks and into our society. You're welcome to join us, to follow us in Geomorphometry at the conference. You will see it. I will have 2 slides from Massi for our Geomorphometry conference, which is upcoming. We're also trying to organize sessions at the EGU, at AGU, if we are there. And we have our coffee talks, and we have our website, Twitter, Instagram, YouTube, LinkedIn, and our data you find on Zenodo. With that one, our coffee talks is now on a regular basis, and here now we even break our cycle of bi-monthly coffee talks, because here we already had last month's one, and now we have one before even our Geomorphometry conference. We run it like that, I introduce you now Yu-Feng, I introduce you to Geomorphometry Society. Then we will have 20-25 minutes presentation from Yu-Feng, and then you have 20-25 minutes for questions, and then we will quickly wrap up here. And we have seen a number of people attending, up to 100 in the past. So it's an open exchange. We respect your peers. Please be kind to Yu-Feng and all that. So the next one where we all want to see you. If you're not registered yet, you can go to with Massi, and you can even chat with him now here in the coffee talk. The conference is upcoming, so 1 month from now, from 9th to 13th of June 2023. Massi, if you don't want to step in and say anything for that one, you can go to geomorphometry2025.org, and you will find all the details from the registration, all the participating organizations. We will have again a demic session where certain people will come, and it will be happening in the beautiful town of Perugia in Italy, where we wanted to have it a couple of years ago, but then due to Corona we couldn't come, and we made it virtually. But now we all look forward to come to Perugia and meet you all there. And with that one, I think that's already my finishing talk here for stop share. My quick introduction here to the Geomorphometry Society. I'm really happy to have you with you today here, Yu-Feng Ho from OpenGeoHub, which is a geospatial analyst there at OpenGeoHub, and he has collaborated with a number of colleagues from even the Geomorphometry Society to develop a global Ensemble terrain model. And with that one, no further ado, Yu-Feng, I hand over the floor to you, and please enlighten us what you want to present here today.
Thanks, Hannes. I'm very grateful for having me today, and maybe I will share the screen first. So I think now you can see my screen.
Yes, Yu-Feng, we can see your screen and we can hear you loud and clearly.
Okay, yeah. Again, I'm very grateful to be here. I think I see so many professors that I learned knowledge from, and then now I on the stage to present about what I was doing in the past two years, probably. So I'm a little bit nervous, so just pardon me, but I will try my best to clarify what I'm doing in this work. So my topic today is about like ensemble, terrain, and derivative in the model for open science community. And what we have now, actually, I want to show these pictures first. This is me. You can see from here. It was back to 2 years ago in the yeah. I was hard to pronounce the name.
Yassi.
Yassi. Yeah, it was back then at the time, and that's why this project kickstarted, because there's a lot of meeting like DMX and all of the presentation I had get inspired of. So this is what brought me here. And this project that we're doing also within one of the European Commission projects, Earth Monitor, Open Earth Monitor, and this is one of our main outputs for like hydrologic and topography to actually showcase that we should go for open data for hydrologic and topographic surfaces. So that's what the mainly support of my my work. And back to the time, this is my boss Tomislav Hango put in here that what they was projected back to 2008, that what will be the future of geomorphometry. And this is how like the schema they're portraying at that time. And he's include himself here, so it took a while time longer than I originally thought, but it looks like exactly what we are looking back in 2008. So now we have you know, the geomorphometry at ALOS. So we have several DTM. We have several digital elevation model. We have several land surface parameters. We have a lot of functional library like GRASS, Saga, Whitebox tool. And now we have the web interface. We have open topography that can interact with the user, and people can reproduce and use all this open data to actually leverage on them for their research. And yeah, and back to in 2003, I have first produced one like trial run for the Ensemble digital terrain model. Was based on very simple 10% quantile, but we were not satisfied from there. So we start thinking that how can we map an Ensemble digital terrain model better from then on. So first we start thinking of that because we see a need or a thing that on all of the community we have multiple global elevation data in fine resolution right now. We in the like 1 arc seconds resolution. For example, the CoperincusDEM, the NASA DEM, the ALOS, the SRTM has been produced in the last 20 years. And so many different sources of the data, they're telling the same thing, but they're slightly different in all of the quality and all of the produced methods, how they kind of sense all this elevation data. And it has been very, very clear that the open database become one of the main supporter for like open science research, because when you have open data, you can derive approach based on the open data, and you can produce. You can reproduce, you can derive more things about open data that thrive the whole scientific community. So we think that this is the way that we should push forward as OpenGeoHub to promote open data, that people can reproduce, people can derive the data product from us, and kind of like helping more in other environmental issues. And also, other than just digital elevation model, we also have a space-borne lidar. They have coverage the whole globe. Also, they have a lot of airborne lidar for sure, for country-based or like regional based. But we're talking here about the global elevation data. Space-borne lidar is one of the source that we also a lot of research that have been used to produce elevation data, even like other height model. So we see here we have at least GEDI and ICESat. If I missed something, please let me know. But these two are mainly the source that we see right now, like very prevalent, that researchers use it as an input to generate the high models or do a validation and stuff. And so that is what they brought me or brought our attention. How can we leverage on all this data to have open Ensemble elevation data from here? So we have all these raster data from the digital elevation model, and we have the space-borne lidar, usually like a point-based. How can we merge or fuse all this data to have a single Ensemble digital elevation model that can be updated and can be kind of like a vampire that exists in the world that for a very long time, like always a single entries for not only for a geomorphometry user, but also for the researcher that didn't have the background of this. They can still leverage on the best data or the easiest understandable data, explainable data to build the research upon. But back to this fusing data, we have to understand also the complexity of and this was also I didn't know maybe that clearly before the geomorphometry conference 2 years ago. I was also not in that kind of like a background, but I learned a lot from there. For example, this paper published by the Professor Peter Goff, to actually explain very clearly, I really it's really must read to understand the differences in the digital elevation model. What is the digital terrain model? What's the digital surface model? This tell me that we can not only have the elevation model don't know what is surface model or what is terrain model, because they are completely different stuff based on the definition. So that's also thinking about how we can actually find not only the surface model from this open data, but also the terrain model that it never happened to be fully opened in a 30-meter resolution. So how can we get the elevation model, which is usually like ALOS and the CoperincusDEM? They are usually, no, they are not usually, they are surface model. How can we leverage on that and fuse them and to generate opened the digital terrain model from the surface model? So that's what we thought that it will be, adding more covariates in the model, try to dictate and try to subtract from the vegetation and the artificial objects like buildings and all this factory and stuff to create single ensemble digital terrain model. So that is what we think that we can use all this kind of schema using a simple random forest model, merging all these digital elevation models and vegetation models or artificial model in terms of the height and the boundary, but also some accessory data like hyperspectral images, like other DTM source from coarser resolution that has been fully open. Yeah, so we thought that would be, I just fit a simple machine learning model, that's not a big deal. So we can produce this math easily. But it's actually not that easy. I was just talk a little bit part of one of the struggle. We have so many struggle, but according to the time schema, we were not able to describe all the struggle that we have. But apparently, like the first struggle we have is actually to digest all this global lidar data that we collected. So this is already the data set you see here, ICESat and GEDI. They're we use the ICESat-ATL08 product and the GEDI level 2, and they're adding together, they are about 30 billions of point. And how can we use this 30 billions of point and to produce a single 30-meter resolution DTM using the machine learning model? We can't really train the model with 30 billion point. Maybe we can, but we are not Google, we are not OpenAI. So we try to find a way that to leverage all this data and to produce one of the digital terrain model. And also, like the digital terrain model in the size-wise is about 200 billion pixels. So which is even like more pixels number than the both of the space-borne lidar both of the space-borne lidar that aggregated. And so the first thing to do is actually we try to find a way to use this data, but the things that we do is to make this data more easier querying. So we do repartitions for the ICESat and GEDI data. This is one of the examples because the data originated from ICESat and GEDI are orbit oriented, and we use the Parquet format to repartitions. And this kind of like algorithm can run in parallel so that we can produce like small tiles of so the spatial temporal tiles of ICESat and GEDI in the small region and small time spent of easier to query. So this is one example that we do to actually first reconstruct the data to be easier to use. And then we train a model using not only the sample from the old global, but also we using kind of like transfer learning or domain adopted schema to get the global model. But in the locally, we add more sample according to the partition that we made. We can add more sample at the local area to create a global to local model. So based on this schema, we produce this global ensemble digital terrain model in 30 meters. And you can find the link here to link to the Zenodo to see our data, but I want to talk more about the result of that. So this is one of the result that we showed in the in our work. So we tiled all this digital terrain. We tiled all the data into small pieces. Sorry, and then we add on the local sample to this to actually enhance the local prediction of the global local to actually enhance the model in the local, adjusting more local context. And so we do this 2000 and 2000 pixel tile, and in total we produce 1,157 tiles with 1,019 extra local model for producing this global ensemble terrain model in adjusting the local context. So you can see that the red square here is actually only the global model type because there's no extra ICESat and GEDI lidar point in there. But the green one is that we have sufficient lidar samples that when the global model has been trained and try to predict in the global tile, we can add more sample to make the prediction more accurate. And this is the result we kind of find in our research. So basically, this is the differences from reference DTM to the Ensemble DTM. And I need to shout out with Peter Goff. He produced this amazing reference DTM dataset that can be easily used as an independent validation for our research. So this is the really good dataset that I really like it. So just to attribute to that. And so using these differences from the global model and global to local model, we can see that adding more sample in the local context can actually increase the accuracy to predict the terrain. So that is one of the breakthroughs that we found in our modeling process. And for sure, we have seen the forest removal and the building removal from our modeling process. But we also see that it's quite interesting to actually found because we are using two different sources of the digital surface model from Copernicus and also from ALOS, we saw that actually the Ensemble, okay, this name is wrong, but we also see that the Ensemble product, they have kind of adopt some attributes, some like features from both model, which is, it's not only just the Copernicus, not only just the ALOS, but it's like a child of them. But also at the different side, we can see that it's actually removing those buildings, but also adapting the feature of both DTM, of both the surface model. And later on that, we also produce data sets for the Geoinformatics 30 meters using Whitebox Workflow. So we create 15 land surface parameters, and we have this collaboration with John Lindsay, and then he kindly guided me to use this software, and then we found out this is quite efficient and also robust to produce all these parameters. And we choose first in this round, we choose 15 land surface parameters, including some local topographic deposition, including some hydrologic layers. And yeah, we are welcome if you have any ideas which layers will be important to serve with the hydrologic and topographic community. We will happy to also produce them and add them to have more surface parameters data set open. And brightly talk about this Whitebox workflow, which is originated also in the core of the Whitebox tool. To someone who didn't know that, but I think most of you already heard about that. For me, the use of the Whitebox, it's comparing to Saga and GraphGIS. It's because of the backbone core that written in Rust, which is quite robust, and memory allocation that John had created is also maybe super handy to use it in the Python environment. And also he has some fast and exclusive hydrological correction algorithms embedded that also benefit a lot that for us to efficiently produce the hydrologic layers. And for produce all the hydrologic layer, we adopted also one of the projection system, ECO7, because they have the they minimize the oversampling of the global land surface and have the correct angle that can produce most of the land surface parameters. So we adapted to this ECO7 projection tiling system in the 600 kilometers, and using as the tile-based process. So that's why we can fit in our memory and execute it in parallel. And we also adapted one of the kind of like our tri-ROM to use the extended tile extent to minimize the edge effect. So for the hydrologic or all original land surface parameters, we path for 16% of the boundary. And it's resulting to like almost 2 times more data operation, but it minimized the artifact that we can find in the hydrologic layer. So that's we are quite satisfied for this process to minimize our edge effect. Also using the ECO7 projection system have one drawback, which is when we try to reproject back to WGS48, we have missing some part of the world because it will be difficult to handle. For example, this area in the Shikoka, because it's really like across 180 meteors line that when we reproject to we reproject back to WGS48, it will create a bounding box that across all this area in this longitude range that will lead to the memory explosions. So it was quite of like a challenge that we are trying to automate the process. And at the end, we create multiple irregular tiles at the edge of the world, and also some irregular tiles in some of the islands that didn't detect from the Eco7 tiling system, and to solve those land missing or projection issues. And it also took some time to conquer that. And also, that is one of the core of the OpenGeoHub, that we have production line. So we have one of the big infrastructure that we have. We have 14 servers and about 3 petabyte of the storage, and we communicate with the open software and using the Docker container to send jobs to different server and collect the computation result that we have the infrastructure to leverage on. So that is why we are able to produce this land surface parameter in 30 meter that you might concern that how this product come from, because we have the infrastructure to leverage on. And we also did a little bit of test of the benchmark for parameterization. So this is the time accumulated in the process that we run in the Whitebox tool. So we first do the try run in 60 meter resolution. We resampled it to 60 meter, and then we run and record all this process for all tiles. So we can find that it's actually about 740 seconds for a tile to run, and then we have in the Eco7 grid we have 781 tiles. So to do some like simple math, like not approximately, it will cost 643 hours to run in one server. And now we have 14 servers in our hands, so it's about 2 days to update 130 meters land surface parameters, the whole data set, in 2 days. That's according to our calculation. And not only we produce 30 meters, we also interested in producing different resolution of the parameters, because it shows that different resolution have kind of pyramids that help for understand the local topographic characteristics. I think you guys have more knowledge than me, but we were thinking that it was a better idea to have different resolution data that can kind of like complement each other to have a complete view of the land surface. So we produce 30 meter, 60 meter, 120, 240, 480, and 960 for our data sets. And this is one of the case that we show in our work. So we do this multiscale topographic random index in different resolution. You can see the details and the interesting things of having all these different resolution end up to be telling different story that can be add on into a complete story. And yeah, and we also have we also wrote a publication together with Carlos, John Lindsay, and then Hannes, and also my boss. So we're currently in the reviewing process, but you can see the preprint from here. And we also have a GitHub that documented this product, and we have also a stack that you can access this product using our stack also, and also put it on Zenodo. But we didn't put the whole data. We didn't put the complete data set on Zenodo. We put the downgraded version. But you can still find the link in the Zenodo description to link to our 30 meters product. And you can easily just click the link and open the QGIS and load this data, the whole 30 meters global data set into your QGIS. So this is one of the example that we also show to easily access. And we also appreciate an open reproducible approach. So we open the GitHub issue that if you have any question or any issue that you spot to add this data, it's very welcome that you report here and we can solve this issue in the very interactive way. And yeah, that's the end of my presentation. But also, as inspired by the story that Tom taught to us, talked to me, what we saw in 2008 is like we need in the future where we have like global geometrical ALOS and the knowledge libraries. I think we have this community serve as a knowledge hub. We have open topography, have the surface, we have the Whitebox tool, GRASS, Saga, and geomorphometry, Julia, and micro DDM that has been served in the software as part of this big knowledge hub. So I think it's actually maybe answer that we are kind of like complete that, and this global ensemble digital terrain model has maybe have a chance to be inside this kind of big pictures to be used and to be kind of serve as the contribution to this community. Yes, that's my presentation.
Thank you, Yu-Feng. Really interesting. I think that was really cool. And thank you for being in time and delivering a really interesting presentation. And I think everybody gives you a virtual clap. I give you a real clap. And thank you for that one. Leave it on. I open up the floor for questions from the audience, wherever who wants to have the floor. Raise your hand or just let me know if you want to have the floor. For the moment, I don't see. Martin, please. Yes.
Hey, Yu-Feng, thanks for the work. Nice presentation. I asked this before, but I'd like to do it in public. Could you maybe make a local drainage direction as well as a derived map? Because you've done the subsequent work, like the stream accumulation, so just the LDD seems very useful as well. And I have a small question about the generation of it. You showed the tiles and including a buffer. So you have big enough tiles to hopefully have the whole catchment. But I think in your example in Europe, you don't completely encompass, let's say, the Rhine or the Danube catchments. So should those tiles be even bigger, or should you have a different tiling system to do the hydrology correctly?
Yeah, it's very good questions. And the first one, you see the field direction, I think it definitely will be the list for the next round. And the second one, yeah, you're right. I think in general that this tile is bigger enough to capture most of the catchment, and even like we didn't see that the issue that very dramatically happened in Europe, but it's definitely some places they could still effect of this. So we are thinking that maybe this approach is it is simple to understand and simple to automate, but it might still have some issue. But we need to really look into something that can be more computing efficient and can also like represent all this catchment. But simply because of this research, we are focused on the production ultimate pipeline. But I think this accuracy, the assessment of this hydrologic layers should be also improved a bit according to following all the catchment. I think right now we didn't see too much problem on that, but it might be, and according to the theory, I think it will be. So we are looking at that, and we were thinking that to have a more assessment and also adapt to a new tiling system if the this current one is not working perfectly. So yeah, we are definitely also working on that. It's not perfect yet.
Okay.
Fair enough.
Thanks, Yu-Feng. Next one, who has a question? Don't be shy, colleagues, today. Usually there's people raising for the floor. If you don't find the button to raise your hand, you can just open up your mic or show your finger up, and then we can give you the floor if you want to have the floor. Peter Strobel from the Joint Research Center, please.
Yeah, hello. Thanks for the presentation. Unfortunately, I missed a large part of it, so that's why I have to ask a rather dumb question. What grid were you using, or are you using for your DTM here?
The grid. What do you mean? What do you mean exactly? The grid is the projection or telling, or?
Well, the projection can be part of a grid. The grid is essentially what are your pixels geometry based on.
ALOS.
Yeah, the DTM production. So when we produce the Ensemble DTM, we use the WGS84 to produce. So the grid is about 1 arc second, but in the lens surface parameters, we reproject to eq7, and we also resample it to 30 meters in the eq7 projection. I think this answers your question.
Well, yeah, eq7 is a good point, but of course it's very crucial then how do you get from the original DGED grid, which I guess you used as an input for at least the CoperincusDEM in that. How do you get through all this? You mentioned intermediate, you mentioned WGS, so that means you had several resamplings. Is that true, and how do you handle them?
Yeah, it's actually a lot of resample. We try to match the grids to create global data cubes. So now we adapted to actually resample everything into 0.00325 degree and 1 grid cell, and then using according to the layers. For example, if I use some categorical layers, we will use the mode. And if we use some numerical layer, we are using QGIS to resample it.
If you go from more or less equal area grids to very non-equal area like WGS, like long-based grids, and back to equal area grids or close to equal area grids, which eq7 is more like, you're getting artifacts in all derivatives. I guess you're aware of that. Is that something you kept in mind, or how are you basically making sure that the data do not kind of get too much alienated during that process?
Yeah, we are aware of that, but we did some visual inspections for the data we got, and for my like maybe some superficial understanding, I didn't see that very severe artifact that happened when we do the reprojection. But yeah, I think the key here is the actual validation of the data set is required. Maybe we really messed up something, but we didn't have the validation for all the surface parameters. So it could be that the thing that we have to work on that to validate it. Yep.
Okay. Thanks, Peter. Thanks, Yu-Feng. Over to Tom.
Yes, hi. Yeah, I just wanted to add something to Yu-Feng's presentation, is that we are in contact with Open Topography, and we are thinking to do a product on top of this, which will take also national data, because many countries have open terrain models, and they are probably better in quality and accuracy than these global data sources. And so we will continue this ensemble also on the national level. And the main framework to derive all the parameters is not going to change, so that will be the same. But there will be just one additional step where we take also national products and combine them locally. So this local global will continue. And hopefully within the next 6 months, we'll have an improved version and it will be published. If I'm correct, Yu-Feng, to recompute everything on our infrastructure, did you mention that? How long will it take to recompute everything from scratch?
Yeah. We are aware of that, but I think Peter's point and Martin's point is about the accuracy and actual kind of
But how long,
assessment for the data
does
should
it
be.
take, how long does it take at the moment to recompute everything?
I think the model is 2 days. Then the parameter is also 2 days, but the model we can still have some improvement that I assume. So
Okay.
now it's about 5 days in total, I would say. But
That's important to know. So if somebody wants an update, it is a large volume of data, so it's really no like not. I think some people maybe analyze 50 meters, about 30 meters. It's not 10 times. So it is a large volume of data, but still we can do an update within basically 1 week or 5 days. So that's why we're now collecting all the feedback and looking at all the other possibilities. And so hopefully as soon as possible, when we get all the feedback and the paper gets accepted, then we will do our one major update.
Okay. Thanks, Tommy. Yu-Feng, maybe you want to stop sharing your screen because you're still sharing your screen now with what's next. So thank you. Then we can see each other, maybe whoever is having up their hand. Who wants still to have the floor? Sorry, there is Yu-Feng. There's a comment here from Yun, sorry for my mispronunciation of your name, Yun Chen. I read it out from the chat. I have checked the paper but found that the accuracy is not as good as the recently released FASM when evaluated with DTM. This works uses a large number of ICESat-2 points for global and local training, but the accuracy is still lower than FASM. Is it because ICESat-2 data is not as accurate as high precision DMs, especially in mountain areas? Yu-Feng, you want to answer to that one?
yes. I think it's Chen Yu probably. So I think the accuracy, yes, as we report, is not as good as FABDEM. We are concerned. We are thinking about it might be because that the ICESat, yes, they have some noise on the ICESat we cannot completely filter out. It's like from the instrumental arrow. Also, FABDEM, I hope that I pronounced correctly. If not, the pet should help. And the fact that they use a computer vision, the model adapting the computer vision concept, that is quite, it's like a hybrid transformer model, which is more kind of like more complex model compared with the random forest. So it could also have a beneficial to detect the heights and predict that. So it was a pretty good approach. And yeah, so this is also what I suspect that the accuracy they have is enough to be higher because we are actually closer to FABDEM, but FABDEM they are better because I think the computer vision model it's performed better than this. So yeah, that's could be that's my conclusion or guess. Yes.
Maybe the colleagues from the FABDEM, I thought I have seen someone from FABDEM before here, could comment on that one as well, but I mean, I don't know if they're still in the call. Oh yeah, Peter, there. Yeah. Go ahead if you want to comment on that
I'm
one.
Peter from Fathom. Yeah, so yeah, I guess as Yu-Feng said, yeah, we focused on the computer vision machine learning method. So yeah, in our previous work with FABDEM, as you say, we used the similar random forest model as you have here, but the computer vision technique basically allows us to take sort of small patches of the DEM, and the machine learning model learns the spatial patterns and is able to basically do the processing on the image as a whole. So it will learn even if the input predictors say are not so good for the vegetation heights and the building heights that you're using, then it's able to still do some adjustments because it knows that it needs to produce some more realistic sort of spatial patterns. So I think, yeah, the computer vision techniques have the power in producing the realistic spatial patterns, which then helps with the errors, I think. So,
Okay. Peter, any other questions from your side? I mean, I think you.
Yeah.
Yeah.
Yeah, it's I'm quite interested by the second the sort of the two-part model. So this sort of global to local model, do you actually, for every sort of local tile, do you retrain a new random forest model for every single sort of small region? So do you have literally 1,000 different random forest models, one for each of your sort of large tiles? Just a clarification on that, because yeah, it's quite a different approach.
Yep, we do, and it's actually not. So we're adapting this one of the technicals, warm starting. So it's basically you have the global model. You just have to load into the memory, and you can retrain it, or like, so for example, you have the decision tree. You have a first 100 estimators to create this decision tree, and then you can add maybe 20, 50 more estimator in the model process, and then adding new sample point to adapt this kind of branch of this tree at the add more nodes at the end of the original trees to create a local model. So, and we try to use this process, and actually in each place it didn't really take too long time, so maybe like 5 seconds to actually add 20, 30 nodes to a local context. But that is what actually we also found that is quite interesting, because now we can have a global model, and then to let different users to add their local data to improve their local prediction, if we have the right infrastructure to string the local data to them, so they can use the predictor to actually predict the local DTM. So yeah, thanks for the question.
Yeah, thanks. Yeah, quite interesting. Yes.
Thanks, Peter. Someone else wants. Tom, you still have your hand up. You still want to have the floor again? Maybe you want to react to some more questions to Peter Strobel's question before.
No, there was a question by sorry, in the chat also.
No, we already discussed that.
Yeah, but it will be interesting if you have any example, like screenshot or something that you discover. Just please send us. You know, we are really trying to listen to all you and collect all the feedback we can. We know we cannot do magic. We are just doing the best we can with the data we have and the tools we have. So of course we cannot do magic, and it is this is an open data project. So you know we cannot use some data sources which cannot be mixed with this data, unfortunately, because they are commercial. But you know we will try our best. Really, if you send us, if you discover any artifact or issue, just please submit it, and we will take it very seriously.
Okay, good. Thanks, Tom, for that one. Any other questions from the floor? And I see that we have. Yes,
can I also add something? So basically, I put the stack OpenGeoHub, one of the example in the chat. So this is what we use as the local tile, because we also found that recently in the global space-borne lidar, we don't have kind of like a spatial temporal blocking for the user to use. So we also create all this. I mean, we call it high quality, but it's actually we filter out some sensitivity issue, some quality flag to help improve the quality of the GEDI, and then we create one of the stack items, like the stack catalog, to host of this data. That if you wanted to use this data for analyzing our DTM, or to produce your own DTM, or produce some canopy high model, this is I think it's a good organized structure that suitable for local usage. And so this is why this is also what we use to actually train this global to local model. It's more like technical details that we had to optimize our process. So you can take a look. I've just put it here.
Okay. Thank you, Yu-Feng. We are coming to the end. I don't see any more questions coming up in the chat. I don't see any hands up. Anyone else wants? Because otherwise, I would like to thank, I will wrap up for today. I would like to thank Yu-Feng for his really interesting presentation, showing us how they have combined lidar and state-of-the-art digital elevation models at 30-meter resolution, bringing global to local models to life. And we had in the discussion some questions on tiling system, drainage direction on DGGS, and all the issues which could happening there. We discussed some difference in methodologies, and even coming up for issues with input data sets which need to be sorted out, if I understood that correctly now. So, and we all heard the request from OpenGeoHub that we all contribute to all the issues found so they can be sorted out in an open manner. And we heard from Tom that they are happy to rerun it at any given moment, or not at any given moment, maybe at one time, if they had sorted out some of the issues which we all discover in the processing pipeline. And I think it's really nice to see that the work from Tom and myself, which we drafted in 2008 on, I mean, that started early on. I think the first draft about the geomorphometrical atlas was, Tom, remind me, 2006 when we drafted that one or something like that. You know, we had the idea. It's really nice that we see it come to life, and even if
We're
it
getting
takes
old,
longer.
yes.
Yeah, and Tommy, we are losing our hair. We are getting gray.
Yeah.
Yeah,
I
you know, but I mean, that's
underestimated how much time it's going to take to get something. But you
exactly.
know, Giuseppe did it about what was it, about 5-6 years ago?
I
You
know.
know, Giuseppe was the first actually to get.
7 years ago.
So some kudos to him, and he did it single-handedly. Now we're a bit more people, I think, and it's almost a whole community.
Yeah.
And so I think we could do it now faster, more effective, and I hope with open topography, if we continue working together, I think world could soon have something really high quality and open.
Yeah, and this brings me to my last point of the conclusion for today. I would say we also need to see that we come and find out ways to automatically evaluate all our products, being it FATOM-DEM, if it's a GEDTM. So we have these networks, and with the DEMX, we have done quite well work to establish the methods, and now we need to bring them to life. Sorry, Tommy, I interrupted you.
Could be on the Perugia, and if it's possible, he could organize some little workshop or training session, you know, for people to use the tools. I don't know if you're in the organizing committee, but Yu-Feng could provide some training session to how to use it and how to access it and things. He has a talk already, I think, set. But if you're interested in Perugia in June, right?
It's the next month, but I mean, Masi is here in we had the discussion on a workshop, and I think I'm not sure if Masi can or wants to bring in another workshop. He's welcome, or if Yu-Feng wants to do, that's a different session. No,
okay.
I mean, I leave that up to sort out between Yu-Feng and Masi if they want to do something.
Okay, yeah.
With that one. Sorry, we are at the end of the time for the day. I thank you everyone for attending for today's meeting, and wish you a nice rest of the afternoon, rest of the day, good night, good morning. Have a how do you call it? A productive day, or hopefully you had a productive day. And with that one, thank you everyone for attending and have a nice day. Bye-bye.